Hello everyone, welcome to the OneClass channel. My name is Fejiro and I'm an honors Bachelor of Science graduate working towards medical school. This evening we'll be going over some commonly asked questions, both at the high school and college level, specifically in chemistry of course. And if you need some homework help or tutoring, check out the links in the description below. And with that, we can start and kick it off with question 1. Let's see here. So we have, let's see. We have, what is a molar mass of oxygen? Okay, so that would be our first question for tonight. Alright, so let's see. Let's review what it means by the molar mass of oxygen. So this question may seem a bit too easy at first glance. First, let's find out what it means so you can get the molar mass. It's usually the atomic mass units, especially when it's talking about an element, oxygen in this case. You just refer to your periodic table, and typically is the atomic mass units, of the element, typically. But in natural environments, oxygen never appears, well, rarely appears like this, okay? So, with that being said though, this is not how it appears in the environment. It actually appears like this, okay? O2 is how oxygen will actually appear in the environment. That is oxygen gas, okay? And you can see in a lot of these gases here, like oxygen, fluorine, chlorine, and such, these elements would appear like in a double. It's like you'll see nitrogen like that, fluorine like that as well. But for this one, we're focusing on oxygen. What does that mean? We follow the same rules of how we used to calculate the molar mass of any molecule, really, where we use the numbers given to figure out how many multiples of that atomic mass we have. So we have, as it says here, 2 times O. That's the only element we're dealing with. So it would be 2 times 15. Yep, 2 times O, which is equal to 2 times 15.999, according to that. Okay. And now, with that being said though, let's see. 15.999 times 2. Okay, we get 31.998 grams per mole. Okay, so this right here, this should actually be the molar mass of oxygen for the first question. Now with that, let's see how we did here. Okay, so this one says the molar mass of an element is equal to its atomic mass. Thus the molar mass of oxygen is the same as the atomic mass, so 15.999. So for this one, I would actually say this is incorrect, because when they ask for atomic mass, that is when you put it straight for the element. When they say the molar mass of oxygen, you have to assume that they're referring to its natural state. That is, I would say this is the trick to that question, because had they specifically said the molar mass of O, okay, which is technically something they can do because that just be an element of oxygen by itself, we could calculate that and it would be 15.999. But when they spell out oxygen, you have to assume that they mean its natural state of oxygen, which it comes in O2. That's how we refer to it as oxygen. Like the oxygen in our environment, that's O2. It's not O. So with that, they mean O2, not the element. Oops. Okay, solution. Oh, frick. Incorrect. Definitely misclicked that one. We'll come back to that later. So let's move on to question 2 now. Okay. So with this, it's asking us the boiling point of water is 100 degrees Celsius. To convert, oh, there it is. What is a boiling point of water in Kelvin? Boiling point of water in K. Okay. So we do have a conversion, and you know, our units in this table right here, conversion factors. So with that being said, let's see what we remember about the boiling point of water. If we typically remember when we discuss boiling point of water, we know that it's usually typically 100 degrees Celsius. That is the common known boiling point of water. But it's not asking for Celsius, it's asking for Kelvin. How do we go from Celsius to Kelvin? Well, with this, you'll see that your teacher professor might ask you to memorize this because it does occur frequently and reoccur frequently in a lot of chemistry equations where you're using Kelvin instead of Celsius. So I do advise that you memorize this, but for those that don't have it memorized, it says here that Kelvins is equal to degrees Celsius plus 273.15. That's what we're going to use here. So Kelvins is equal to degrees Celsius plus 273.15. Okay, and that's how you get to Kelvin. So now let's plug in our number. All right, so now we have 100 plus 273.15. Okay, so that means that the Kelvin amount for boiling point of water would be 373.15 Kelvin. That is our answer for the boiling point of water in Kelvin. Okay, that's what the K stands for. So exactly, this one they do use 273 instead of 273.15. It's mostly the same. Exactly, and they even mentioned that they use that as well. So it's really up to you, specifically up to your professor / teacher, whichever one they add onto the conversion sheet, or whatever your textbook mentions as well. But that 273.15 is something you do have to get familiar with because it does reoccur often in chemistry questions. Alright, let's move on to question 3. What is a molar mass of calcium phosphate? So molar mass of calcium phosphate. So this one's a little bit tricky here, because you kind of have to know, I mean, most of you hopefully should know what calcium is, but for this one you also have to know what phosphate. I'm not actually underlining the red because that one is just straight from memory, at least that's how I familiarize myself with them. But yes, so let's move on to at least the things that we do know. So calcium, let's go all the way here. As you can see, it's an element that we can just write down. Alright, and how many electrons would it like to lose? Well, we can figure out 2 ways. One by its column number, which is 2 in this case. And the other way, actually, by its electron configuration. That one I do like to use sometimes just to be able to review electron configuration. So it's good to get really familiar with it. So considering it's on the 4th row, you're going to start first with the 3rd row noble gas, so that's argon. Okay, and then you have 4s2. Once again, emphasizing that it does want to just get rid of that to become a quote-unquote noble gas. So typically, calcium will be Ca2+ as an ion, which is what you want to make up for this calcium phosphate, which is an ionic compound because it has a metal and a non-metal. So with that being said, what's phosphate? This one is a little bit tricky. Phosphate, because it ends with the ATE, okay, is a phosphorus, yes, and a certain amount of oxygens, okay? So that'd be phosphorus P and a certain amount of oxygens O. Alright, and as I said, these are the things that you kind of have to memorize, because I know that phosphate comes like that, PO4. That is phosphate. And with that, you also kind of have to memorize the charge, because it's not so clear when you just look at the element. At the molecule, because oxygen typically likes to have a -2 charge. We're just talking about the net charge here. So if we did this -8, phosphorus, oh wow, I guess it does make sense because phosphorus is the 5th element. So maybe it likes to do the +5. Okay, because that makes sense because PO4 is actually 3-. So I guess there are ways to figure it out like that. But I can say right now that that may not be the best way to go about it, but it might be a start. I'm going to star that because I might use that for later examples as well. So with that being said, we have PO4 3- and Ca2+. Okay, so what do we do with this? We want to make sure we balance out to where they have a net charge of 0. Okay, so that means we need to find the lowest common multiple between 2 and 3, and that would be 6. So for this, we would actually need to multiply this by 3 and multiply this by 2. So in total for calcium phosphate is Ca3PO4 2. Now we've done all that work now, but we haven't actually figured out the molar mass. Give me a second. Let me just actually put this in my calculator and see what I get. Just working ahead, but just as we did for the earlier question, actually, what we want to do here is that now we want to break it down into its pieces, kind of like the O2, but there's obviously a lot more components. So 3 times Ca, okay. Now with this 2 here, you want to make sure you multiply both by 2. So we have 2 for the phosphorus and 8 for the oxygen, okay. So 3, 2, and 8. And now calcium, okay, is 40.078. Phosphorus is 30.974, and oxygen all the way over here is 15.999. So now we have to really multiply those all together and then add them after. So 40.078 times 3, 120.234, and then 30.974 times 2, okay, is, let's see here, 61.948. And now for the last one, 8 times 15.999. Alright, we have 127.992. Okay, so with that all being said, we add them all together. So now we have that plus the 61 plus the 120. Our total is 310.174. That's not a good one. There we go. Alright, so that means that our molar mass in total is 310.174 grams per mole for calcium phosphate. So that's a really big molecule compared to the other ones we deal with. So exactly, let's see what they did here, and they do get around that number. You can see that the phosphorus value and the oxygen value and even the calcium value were slightly different, but exactly they should have gotten, which they did, answer that's close to mine. So 310.18. So with that, just a quick review. We first broke down what it meant to be calcium phosphate, okay? And then we found the molecular mass from there, okay? Alright, so now, let's see. Our next question, question 4, is SF6 polar or non-polar? So now for this one, this is a very fair and interesting question because it definitely comes with a few layers to it. The first thing we need to do actually to find out if it's polar or non-polar is to actually draw its Lewis dot diagram. So considering it's SF6, let's just draw what we do know. So let's just start with how many electrons they have in total. So we have first sulfur, okay, and sulfur likes to have 6 electrons, okay. And now, with that being said, fluorine likes to have 7 electrons, but there's 6 of them. So in total, we'd have 42 from this side. So in total, between the 6 and the 42, we have 48 electrons to account for. That is quite a lot. So with that being said, let's go ahead and get things moving in regards to that. Yeah, so 48 electrons. Now let's see what we do. We put the sulfur in the middle because that's really the only point of basis we have, and after that we kind of try to surround it with the fluorines. Because it's 6 and sulfur just happens to have 6, it's one of those rare, I guess, elements that doesn't mind having more than 8 electrons in its valence shell. So it breaks the octet rule. So actually, I'm going to add that note. This breaks the octet rule, okay? And now, with that being said, let's go back to this and keep filling out the sulfur. And bam, looks quite messy, I know, but this is just kind of to get the visualization of what the possible Lewis dot diagram will look like. So as you can see, I'm filling in every single electron there is, and we're almost there. There we go. So this is the Lewis dot diagram, okay? So now with that being said, we kind of have to navigate and count all of these, but we know that each one gives us 8. So 8 here, 8, 8, so that's so far it's 8 times 3, 8 times 4, 8 times 5, and 8 times 6. And we know that 8 times 6 does indeed equal 48. So we have the right amount of electrons there. So now for this one, You can kind of start to tell whether it's polar or non-polar, considering it has literally no other space to do anything else. But actually, I do have this handy page here, which sometimes you are required to memorize. But if we scroll all the way down our VSEPR theory, so actually before we do that, you notice where it says electron groups, okay? That is the number of pairs you have, whether they're lone pairs or in a bond. So sulfur, okay, its electron group is 6. And most things like to have an electron group of 4, because that's the octet rule. 4 pairs, 8 electrons. But sulfur is like, yeah, I don't really care about that. So that's how we got there. So when we scroll all the way down to 6, and if we have 6 bonding groups, which is what we have, 6 bonds here, and 0 lone pairs, is an octahedral, okay? So if we drew it out in like open space, this is kind of what it would look like. Sulfur being in the middle, okay? And with fluorines just in every corner here, right? And each angle is a 90-degree angle. So no matter where you look at it, there's a fluorine 90 degrees away from that fluorine. So because of that, okay, you can say that they're pulling just electronegativity, even if it's just slightly, they're all pulling equally in directions that end up canceling each other out. So this would be like the forward and back, and this would be up and down, and this would be left and right, okay? Everything is equally being pulled in every direction. So to answer your question, if it's polar or non-polar, sulfur hexafluoride, which would be a name hopefully, monosulfur hexafluoride would actually be non-polar. Now, there are many ways you could have figured this out. The valence gives us a hint, because when you draw the Lewis dot diagram, if you see like any lone pairs, you almost are notified right away that it is going to be a polar molecule, because that electron, that lone pair, likes to do a lot of the work and pull towards that direction. But when you see that there's no lone pairs, you compare what's bonded and consider that everything here is a fluorine. That means everything here has the same amount of electronegativity pool. So that 3.98 minus the 2.58 is going to be the same for every direction, which is why it's a non-polar molecule. Now, interesting enough, this is a perfect example of a non-polar molecule with polar bonds. I'm just mentioning this because some questions might even ask that too. The reason why I say it's a polar bond is because, as I mentioned, the electronegativity. When you do the electronegativity of fluorine minus sulfur, and you look at the values, 3.98 minus 2.58, (1.4). Okay, and right there, if there's a question that actually asked for this, I'll explain it in further detail, but that falls in the range of what is considered a polar bond. So yes, all these bonds are polar, and they do have an electronegativity, negative electronegativity going out, and the sulfur is a positive one. But because they're all pointing the same, not the same, in equal and opposite directions, that's why it's non-polar molecule. Okay, so let's move on to question 5 then. Let's see actually what they say first. Exactly, it's a non-polar because VSEPR theory. So there was 6 fluorine are arranged symmetrically. The bond dipoles are cancelled. So they do mention that the bonds are indeed polar, and because of that, it's cancelled. So this is correct. All right. So let's move on to question 5. Okay. The specific heat of gold is 0.129. So gold specific heat is 0.129 joules per gram per degree. So every degree increase. Now they want the molar heat capacity. Okay, so you're probably wondering, which actually I did it first, how do you even get there? But the answer actually lies in the units of the specific heat, specifically this unit here. Right now that's in grams. So in a sense, what this question is asking for is the specific heat, but instead of it being measured by per gram, they want it per mole. So now you're probably also wondering, how do I make that change? So let's use our rules in terms of like numerator and denominator, and then let's use what we've learned so far in terms of when we want a certain unit canceled, we have to put in the opposite place, whether it's numerator and denominator, from what it was originally at. So the one thing we do need is that we need the molar mass of gold, which in this case, because it appears in the nature as just gold by itself, it's just going to be the atomic mass unit. So if you look at the periodic table here, gold is all the way down here, and the value is 196.97 grams per mole. That is the molar mass of gold. Okay, so now that we have that, we want the specific heat, but in terms of that in molar, right? So we first write down what our specific heat is when we're using grams. So 0.129, okay, joules, and then we do this to make it easier for us to write, per gram per times degrees Celsius. And now we want to cancel out the grams. So actually what we'll do, okay, so do it like that. So grams needs to go on top. So we have 196.97 grams per mole. And now, bam, these two cancel out. And if we multiply 0.129 times 196.97, we get 25.41. Let's round there, okay? But now you notice, okay, so what would the units be? It still has the joules, it's still over Celsius, but now it's over moles as well. So look quite similar actually. It will be joules per mole times degrees Celsius. This actually would be our new molar heat capacity, because now it's saying for every mole and increase in 1 degree Celsius, the amount of joules it will take to increase that gold will be 25.41 joules. Okay, and wow, perfect. That is exactly what we're able to do here. And exactly, the only thing I would stress really is to make sure that you keep all your elements. So exactly, they do have degrees Celsius there. I'd always put that there just because, you know, on the off chance then they say, oh, there was a change in like, you know, 20 degrees, and then they ask you to calculate the amount of joules from there. It's just good to have that unit there so you know how to factor it in. But other than that though, this is correct. So with that, let's move on to the next question. Question 6. So now this question is asking, what is an alkoxy group? Okay, so this is kind of more so a review of like organic chemistry. Unfortunately for these, it just really goes down to memorizing and, you know, implementing, but we can try to break down the words so that way at least we get more familiar with it, because as you see here, you see oxy, okay, meaning that this group, okay, will have some oxygen, okay, and what do you see here? ALK. Now this can mean like alkene, alkyne, but point being it's some type of alkane, some like carbon hydrogen chain. Okay, but we don't know what it is, so that's what we designate as R. Okay, so this actually in a sense is what an alkoxy group is, but you cannot forget that it actually is going to be bonded to something else. So that's what it would look like, but this part here is what they refer to as the alkoxy group. Because like let's say for example you had CH3 here. This is the alkoxy group, okay, bonded to methane. That's how you would describe it. If you had, you know, this same thing, this is the alkoxy group bonded to ethane. Now the reason why I'm drawing these, because as you see in actually like when they explain the answer, they are named in specific ways. The alkoxy group, so the part, usually they pick the shortest chain to attach to the oxygen, but that one is referred to as like your that was referred to as, yeah, exactly, as your alkoxy group. So let me give you an example of some I believe there'll be ethers if I'm not mistaken, but I'm not too focused on the name right now. We just want to make sure we get the or the name of the whole compound. I want to make sure we get the name of the parts down. So if I do an element like this, okay, alright, so now we have to make sure we count 3, okay, and then we have 1, 2, 3, 4. So this one, okay, 3 and 4, we want to make sure that we still have our group. So this right here, the longer one, will be known as butane, and the shorter one actually is known as propane. So what we do, okay, we want to drop the A and E, like the propane part, and change that to the loxy ending. So we'll actually have propyloxy, so I can write that better, propyloxy butane, okay, and that will be the name for this compound. But the thing that they're focusing on is the alkoxy group. That would be the propane plus the oxygen. And just to make sure that I am saying that right, let's see, propyloxy butane, okay. Oh, propoxy butane. That does sound a lot better. Let's see if this, yep, there it is. 1, 2, 3, oxygen, 1, 2, 3, 4. So I have to fix that name real quick. So I guess I dropped out the wrong part. It should be at the pro part, not the prop. So it'd be prop. How do they do it again? Prop. As you can see, I need to review this as well. Propoxy. So no propoxy butane, just like that. Oh, I see. Okay, that makes more sense. So with that, that is an example of an alkoxy group. The main focus is that usually it is a shorter chain when you deal with simplistic things. I mean, things that are more simple. Or it can be like, for example, if you have a phenyl ring, okay, and it's attached to like that. Usually, because the phenyl is like the main part, you'd want to say that's your alkoxy group there. So, because it'll be a lot hard to name whatever this would be with the oxygen. So, with that being said, hopefully that covers it. The main point being is that when you see an oxygen between two chains, like just the chain attached to the oxygen and then another chain continues, that is a form, you have an alkoxy group there. But the thing you should watch out for as well is that when you see something like this, And I know I mentioned that could be an ether, but this is something you should watch out for, where you have, okay, this right here, that's an example of an ester. It's when you have an alcohol group and a carboxylic acid bond, and this is usually what it results in, if I remember correctly. But the point being is that it does have a different type of naming. I just wanted to clarify that even when you do see an oxygen there, you want to make sure there's no like carboxylic acid right above it here. You want to make sure it's just the oxygen. So if we were to draw that, you want to make sure it's just that. Okay. So with that being said, this is not an example of an alkoxy group. You may be able to say maybe this is, but I wouldn't trust that. I'd look for things that more look like that. Okay. Yeah. Technically, this would be viable, but just be hyper aware of the carboxylic acid, because it would definitely not be named like this. Okay. So now let's see what we have for what they said. Yep. RO, exactly what we have up here. RO, and exactly the alkyl group, and it's attached to oxygen now, exactly. So with that, let's move on to, this is correct. And now let's move on to question 7. What is the name of the compound with the formula NaF? So, name of compound with formula NaF. That's a great question. So first we need to figure out what this compound is made of. We see Na and we see F. So let's go to the periodic table to find out what Na is and what F is, okay? So let's start with Na. As you can see here, Na is sodium, okay? It is a metal. And that's really all the information we need here. The key thing actually being that it's a metal, okay? Now let's go over to F. F is fluorine, okay? And key thing is that it's a non-metal, okay? So now we have this compound, and now we know that it's a bond between a metal and a non-metal, okay? So there is specific ways to name this. Now the most important part actually is that when you, sorry, I blanked out. The most important part is that you have to recognize what type it is. Because you have a metal and a non-metal, that actually is an ionic compound. Because you have a metal and a non-metal. And ionic compounds have a certain way to be named, okay? You start actually first with just the sodium. You don't change anything. And you actually then get the fluorine, fluorine, okay? But you stop here actually. The INE in this gets dropped and gets replaced by an IDE, okay? That is actually just the, I guess, the simplistic terms of how you name ionic compounds, okay, when it's just a metal, non-metal. Specifically the elements though, because like when we look at the previous question when we did calcium phosphate, it wasn't calcium phosphide, for example, because the 8 implies there's oxygens with it. So if it was calcium phosphide, which I don't think I've ever really seen, that one would just be CAP, like that, something like this, and then it'll probably have the same like Ca 3P2, but I've never seen this molecule in nature before. It may exist, but yeah, that's just an example. The ending of the ionic compound is very crucial in understanding what type of compound it is. So for this case, when they said NaF, the ending is just IDE. Okay, let's see if we got that correct. Exactly, we identified it. We said it was an ionic compound, and because it has metal, non-metal. So exactly, you want to drop those 3 letters and replace with IDE. So we have sodium fluoride, and that is indeed correct. Okay, so we move on to question 8 now. It says, consider this initial rate data at a certain temperature for the reaction described by. So initial rate data at certain temperature for this reaction. Okay, we have N2O3 gas is equal, turns into NO gas plus NO2 gas. Okay, and then we're given this table, which is actually very crucial to answer this question. We have now the concentration, the initial concentration of each of N2O3 in different well, we have N2O3 in different concentrations, and C, and here they give us the rate of the reaction based on the different concentrations. Okay, so N2O3, C is the, what is that? So that's exactly at the beginning, so they have 0, and exactly we want the concentration of it, and then we have initial rate. Okay, alright, so now we have 0.100, 0.200, 0.300, okay, and we have 0.630, 1.260, and 1.890. So now that we've written that out, determine the value and units for the rate constant. So for this, what the question is asking really is, what is the relationship between increasing the initial concentration and the change in the initial rate, to find out how the rate law works. So for this, to find out actually the ratio, what we do is we take one concentration. Actually, we perform ratios here, but point being is that we do 0.100, that concentration had 0.630 of a rate, and 0.200 concentration had 1.260 of the rate. Okay, so if we did some moving about here, okay, well actually we don't need to move anything actually. If we just divided by each one, we get that these two equal each other actually, because when we divide this, exactly, this is just double. This right here is 2 times what happened here, although they're the same thing. Point being, actually, let me actually rearrange this to where it makes more sense. Let me put it this way. When this was doubled, okay, this was also doubled. Okay, so 1 led to that and 2 led to that. Okay, so this is just 1 times and 2 times. So right here you can kind of say that this is going to be, you know, it's a 1-to-1 relationship, but we want to make sure that applies to everything going forward. So this is the 1 to 3 jump. Okay, So we have 0.100 and 0.300. Okay, and we now have 1.890 and 0.630. Okay, and if you actually put this in your calculator, you see that this is actually now 3 times. Oops, 2 times here. 3 times there's the relationship here. Okay, so with that being said, now if you drew a pseudo graph, right, it will kind of look like this: 1, and then when it was doubled, 2, and was, you know, tripled from the 1, 3, and you have kind of a straight line. Okay, oops, let me just draw like that. All right, so with that being said, this is a linear relationship, not an exponential relationship. So that means that the rate is going to be to the power of 1, because the power of 1 is what implies a linear relationship. So really, you have rate K is equal to the concentration of N2O3 to the power of 1. Well, actually, sorry, it's going to be rate, I believe there's something before that. Something times the rate is equal to that, but let's see here. There we go. Yes. So rate is equal to K and 203 1. Okay. And the reason why we figured out 1, well, M equals 1, is because of this relationship here that we established. Every time we went up by a certain amount, the rate went up by that same amount as well. There's no like exponential growth or even logarithmic growth or anything like that. It was just 1 to 1. Okay, so let's see here. Yep, they show here that it was a 1 to 1. So the first order, and exactly. But they do go forward in terms of establishing what the actual rate is. Well, I mean the K. Let me see if the question is asking that. I'll determine the value and the units of the rate constant. So they do actually ask for that K. So the way they solve it there, actually, as you can see here, you can actually use, not even establish a relationship, and you notice M is equal to 1. You use any of the values there to find out what K is equal to. So we have the initial rate, so let's actually use a 1.260 is equal to K times the concentration of N2O3, which was 0.200 at that time, okay, to the power of 1. And we know if it's to the power of 1, it's just 0.200. So now we divide both sides by that number. Okay. And let's see what we get. 1.2. We get that K is equal to 6.3. Okay, but now there's actual units. Okay, that's the part you can't forget. And because we know it's a first order reaction, okay, this is a part you kind of have to memorize, unfortunately, because each 0th order, first order, and second order each have different units for their constants. But for the first order, it's just going to be S minus 1. That is what we get for the constant here, the rate constant. Okay, so with that being said, let's see what else we can do here. How do we do? Yep, 6.3 negative second, well, the inverse of seconds. That is all correct. So with that being said, this is indeed correct, and this is how you solve question 8 here. Let me just make sure we go over everything. Exactly, we did establish the relationship. We know it's linear, so it's first order. And then with that being said, using that, we found out that the K value is 6.3 S to the minus 1, seconds to the minus 1. So let's go on to question 9. Depict electron configurations for each of the following. Wow. This is gonna be a long question. Good. Let's see. Hopefully you can sit with me type through this as I solve this question. So depict electron configuration for each of the following. I'm just gonna write everything down here. So we have A is chromium, chromium 2 plus, and chromium 3 plus. B is copper, copper plus, and copper 2 plus. C is vanadium, something like that. Vanadium 2 plus, and vanadium? No. 3 plus. So those are the ones that they want us to do. So if you're worried about not getting enough electron configuration practice, well, there you go, because this is going to be a good amount of practice here, so we can get extremely familiar with this. So with that being said, okay, let's see what we have here. Let's start with chromium. Okay, for this, as a disclaimer, I am going to use a shorthand for electron configuration. Now, if you don't remember me saying it, is that you want to start first with the noble gas from the previous row, and then you just go on as normal. Okay, because you know, to get to helium, it's 1s2, that's helium, and then neon is 1s2, 2s2, 2p6, and then argon is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and that's, I just wanted to set that up there because just in case we were wondering. So let me actually put this here. That's helium, this is neon, and this is argon. Oops, AR, not silver. So with that being said, this argon, and now we want to do chromium first. Okay, chromium is right there. So what is V? Oh, vanadium. Oh, it's close. Probably butchering that name, but exactly. So chromium is going to be 4s2, because where we started, the fourth row. But because you got into actually now the D subshell, okay, this we want to actually subtract. You want to subtract 1 from the row, I mean from the number, so you actually have 3d4. Okay, but we're not done here actually. So for the D shell, it's actually better if you look at the orbital notation for this, because considering that it's 3, you actually want to put it first, but D orbitals actually need to have 10 filled, and then we have the S orbital here. So we have 3d, 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 4s. Okay, and we have, as I said, 4. And then we have this. As you can see, that's kind of greedy of the S row, especially when you're dealing with D orbitals. The change from the D to the P or the S shells, there is quite a bit of energy difference. So for an actual more stable element, I'd actually prefer to have its D subshell at least filled with 1 electron than just conveniently doing, like, you know, having the 4s2, because that is exactly, it is quite greedy for this S. So what happens here is that this one electron would actually move and would actually be placed over here. This would actually stabilize, at least for the orbital notation. This would actually be a more stable chromium. So if we actually rewrote that, it would actually be, again, starting with AR, okay, will be 3d5 4s1. This right here is chromium. Okay, so now let's think about this. What happens if we lose 2 electrons? It would most likely want to lose it from its most outer shell, And considering that the most outer shell is this, I'm gonna actually have to use maybe a pencil to kind of cross it out. This will be the first one it loses, and then it'll lose one of these. So chromium 2 plus in that case, okay, would be AR, still starting with silver, but 3D 1, 2, 3, 4. And then if it was chromium 3 plus, same concept, but this side has now lost this one as well. So it would be AR 3D3. Now I do want to just make sure that at least we're solving this correctly, so let me just double check here. Yep, 3D4, and they do actually mention that you know, it's gonna be 4S1 3D5 because of the whole orbital notation as I showed. That's good. And yep, 3D3, perfect. So with that, we can kind of box chromium, knowing that yes, we solved that correctly. So now let's move on to the next one they talk about, copper. So copper is also on the 4th row, so you can actually start with silver again. Okay, copper, copper plus, and copper 2 plus is what they mentioned. Okay, so we have the same thing here. So first, let's start our mock work up here. It's going to be that argon again, 4s2. Okay, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 3D9. Now this one's a little bit trickier, but it actually follows a similar situation as the one shown earlier. It's still in the 3rd subshell, so it actually would prefer to be the one that's filled, because if we drew out the copper one, okay, using I guess the one we have here, okay, we have the 4s2, okay, whoops, facing the opposite way, but 3D 9, so we have, it's literally almost there, just missing this one right here. Okay, so what it would actually do is that it would take this one and place it in this row, only because exactly we're still in the 3rd subshell, so exactly the energy difference is significant enough to where that would be more stable. So for this we actually have AR, okay, 3D10 4S1. And now you actually see why it would be easier for copper to just lose one electron. Well, I mean, it can, because it's a transition metal, it can actually kind of choose which electrons to lose. But you see here, it will be 3D10 by itself, because all I just did was get rid of the 4S1. Okay, and now for 2 plus, this one is a little bit trickier, but I just want to say that if you just lose another one, I'd prefer to keep everything still in its 3rd subshell, so just be 3D9. Now let's see how we did there for that one. Okay, yep, 3D10 4S1, so we're on the right track. 3D10, okay, my moment of truth, 3D9, whew, good. So I guess the lesson here as we're going through this is that you wanted to get rid of the higher number of electrons first, so like in the higher shell, orbital shell, and that was a 4, hence why it was having an easier time getting rid of the 4s1 first. Okay, so now with that being said, let's move on to vanadium. Okay, so hopefully this time we won't have to self-doubt ourselves. Let's see what vanadium is dealing with. Okay, so vanadium is, let's erase these and see exactly, oops, what we're dealing with here. So the scratch work here Vanadium starts with AR like the rest of them. Okay. And it'll be 4s2 3d3. Now this one is a little bit tricky because it's not like 3d4 where it's super close, but is it close enough to where it wants to because exactly the difference still is that I mean, some things will still have the same orbital notation. The difference being exactly is how many protons they have. So there's still, remember, there's still different elements. Okay, so I'm gonna go on a limb here and say that it would still prefer everything in its D subshell. So for V2 plus and V3 plus, I believe that's the ones that they wanted. Let me see. Yep, I'm gonna go on a limb and say that we have still the silver, but it wants to stay with the same electron. Let me see here. So if we have 3 here and 4s2, as I mentioned, that's extremely greedy, so both of these actually would have to leave. So it just kind of balances out the third subshell, kicking those two out. Give me a second. This is so far my theory, great, based on everything we've done. So hopefully it does follow that trend. So it'll just be 3d5. And as I mentioned, because these elements do have different protons and such, you don't have to worry about them looking the same way, because the fact that, you know, it's not the same elements, different protons, different neutrons, so the electron configuration, it's the part that may seem similar. So 2 plus, it will just be 3d3, and 3 plus should be 3d2. Let's see if that's correct, or if it just broke that rule. Oh, it did break the rule. Interesting. I guess when it's not close to filling that shell, it doesn't bother moving. Interesting. So 3D. So I guess the rule is based on, I guess, as you see here, when there's only one difference, because it still doesn't want to completely lose its fourth orbital just yet. So just like if it's cost effective, because I think if I remember correctly, it wants to be able to fill each subshell group at least one electron. So if I had to get rid of both from the fourth one, then it's already expending a little bit too much energy to try to balance itself out. So it would make sense to why it would want both to just stay in the 4s. So it would be 3d3 4s2. But it also explains why I can get rid of the no, this is the tricky part. It explains why I can get rid of the fourth subshell so easily. Now for this one, actually, I'm thinking that this one, instead of it being just getting rid of the 2 shells here and that, it might actually just end up being 4s2. It might have just gotten rid of its third orbital. Not sure. This may be incorrect. I'm gonna start and we'll see. Yep, 4s2, 3d3, okay, 3d2. I see. So it kind of just keeps shedding from the outside in then. Okay, that makes sense. So this will be all for vanadium. Definitely the trickiest one of the bunch, because I think this is the part we have to really understand, is that as you see here, if there's going to be too much energy used to try to fill up both shells instead of just one, like it wasn't just missing one, it was missing both, kind of like what we did with chromium, it'd rather just stay in a spot. So that's what we have here. But when we do start getting the ions, it'll just shed from the most outer shell. So the 4s2 will be the first to go, then it'll just lose another one from the third subshell. Okay, so with that, this is correct. Okay, definitely a much heftier question. Glad we were able to get our electron configuration practice in, and now this question is asking another electron configuration question actually. How many electrons can S, P, D, and F hold? Okay, so with this actually, there's multiple ways to figure this out. If you can't remember the formula or anything like that, then it might be tricky for you to remember. And for those people out there that aren't really good with formulas and such, I actually recommend that you then use this trick instead, going through the periodic table. Okay, so we know helium, right, is 1s2. Okay, so helium, okay, is 1s2. And as we drew our s orbital up there, right, it was just the s like that. Now actually, let's do something real cool real quick. You see where the helium is? Imagine the helium was like right here, okay, above where the atomic symbol is. We have 1 electron, 2 electrons, hence why we have one box but with 2 electrons in it like that, spinning in the opposite direction of each other. So s orbitals, as you saw when we were doing the later question, we did the 4s2, can only fit 2 electrons, and is also based on how many jumps you make. So you see 1, 2. Now with the p orbitals, that's the one that comes next because these are the ones over here. Okay, and remember how we're talking about argon was like 3p6 is because you have 1, 2, 3, 4, 5, 6. So it would look like, I'm going to use every different color here. Okay, so with that, this is s orbital, this is the p orbital. Okay, there we go. And now, okay, we're going to now figure out for the d orbital, okay, because now we know this can hold 6. D, you refer what we were doing earlier when we were dealing with vanadium, chromium, and copper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I remember how I drew 5 boxes up there. So we have 3, 4, 5, okay? And exactly, it counts exactly with the periodic table in terms of how many elements there are. Now, with the final one, the F subshell, okay? 3, 4, 5, 6, 7. Reason why, because let's actually count. We don't count lithanium or actinium because these are their series. They would technically go here where the D shell is. So actually we start where cerium is, okay? And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that matches perfectly with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So to answer your question of how many electrons can the S, P, D, and F fit, it will be 2 here, 6 here, 10 here, and 14 here. Okay? So now another cool way of knowing this is that each orbital is technically how do I put this, is assigned actually, like when we talk about the L, that's refers to the shell. Okay, let me use, I guess I'll just use this color. Okay, the L refers to the shell. And for the L group, okay, S orbitals are 0, P are 1, D are 2, and F are 3. If you want to know how many each of those can fit, you use this formula, okay? 2L plus 2. Okay, if I remember correctly, because considering this is 0, okay, 2L, whoops, I think it's 2L plus 1, like that. There we go. Exactly, L is 0, so we replace it with L. So when the shell is S, that means it's 0, so we get a value of 2, which checks out. When it's 1, we now have 2 times 1, which is 2, plus 1, which is 3, times 2, which is 6, which also checks out. And then if we're dealing with the D shell, which is a L of 2, we now have 2 times 2 is 4, plus 1 equals 5, times 2 equals 10. That checks out. And now for the F, is 3, so 2 times 3 is 6, plus 1 is 7, and you get 14. That checks out too. So this formula here is actually quite handy in figuring out how many electrons will be in that shell, as long as you know actually what the L refers to, if they're talking about the S, P, D, or the F shell. Okay, and look at that. Yep, the 2L plus 1, which is the form we have here, and S2, P6, D is 10, and F is 14. Oh wow, I put 0, 1, 2, F. I don't know why I did that. 0, 1, 2, 3. There we go. And yeah, that is the breakdown, and also this shows the orbital notation of each row. So hopefully that answers your question in terms of how many electrons can S, P, D, and F hold. So with that, this is correct. Now let's move on to question 11. And while we're on question 11, we're going to take a quick water break. I don't get too parched. Okay, so phosphoric acid, H3PO4, is used to make phosphate fertilizers and detergents, and is also used in carbonated beverages. What is the molar mass of phosphoric acid? So they were really kind here to just give us the molecular structure of this. So with that, we can really just roll with that and answer the question. So as I discussed earlier, though, when you're dealing with, actually it's technically not phosphate, but it's actually things that end in 8. So like phosphate, for example, the ion, PO4 3 minus. Well, first, actually, let me write the question. I'm jumping ahead. So, what is the molar mass of H3PO4? Okay, so like I was saying, when you have an ion that ends with 8, right, when you turn that into an acid, you delete the 8 and add the ic followed by acid. Okay, so phosphate became phosphoric acid. Okay, well, it technically added the ORIC, but point being is that what does it mean to add acid? You just need enough hydrogen ions, and because it's 3 minus and each hydrogen was just 1 plus, you need 3 hydrogen pluses, which is exactly what we have here when we have H3PO4. That's just for you to get familiar with the naming, in case this question decided, you know what, I'm just going to give the name and you figure out the molecular structure. So with that being said, now that we have that, we need to figure out the molar mass. So we need to just break it down as we've been doing. So we have 3 hydrogen, okay, 1 phosphate, and 4 oxygen. Okay, and let's see here. We have for hydrogen, it's 1.008 for phosphorus is 30.974, and for oxygen we have 15.999. Okay, so that's 1.008 times 3 is 3.024, I believe. Yep. And then we still have the 30.974, and we have 15.999 times 4, so that's 63.996. So all of these get added together, plus 30.974 plus 3.024, we get 97.994. So they might have rounded their answer, but this is going to be the molar mass of phosphoric acid. Let's see how we did. 1.01, yep, they have slightly different numbers. 30.97, exactly, slightly different. 16.00, and they did the whole 3 of them. Yep, 1 of them and 4 of them added together, and they did get 98 grams per mole, which is what I had a feeling based on how they were rounding theirs. So this is a quick disclaimer. Exactly, you're going to solve it based on the periodic table you were given. If you weren't given one, then the teacher can't fault you for having slightly different answers from them, because periodic tables, they do try to be standardized, but they do each one can round a little bit differently, hence why they have slightly different numbers. Okay, so that is correct. Let's go on to question 12. Okay, what is the definition and equation for molality? So maybe you already saw the answer before I can switch it over. So definition and equation of molality. Okay, so the one that I'm actually quite familiar with, because I'm gonna be real honest here, I rarely see molality being used. Most of the time we base it on molarity or the concentration. So when we have molarity, okay, and the reason why I explain molarity, because it helps you tie it with molality. Okay, so you have molarity, the big M, right? Okay, that is actually the moles per liter. This is molarity. And what is it? What is the definition exactly? It's how many moles of a certain compound or element are in 1 liter of typically water. That is the molarity. Okay, now for molality, okay, this one still has the moles, and you signify it by the small m. Okay, but instead of it liters, it's kilograms of water typically. So they both say fairly similar things, as in they're both trying to say the kind of the similar thing, but one is per liter and the other one is per kilogram. And depending on, I guess, the kilogram, whatever you're mixed with, I believe it's typically water, because that's the typical aqueous solvent you want. But they do end up being fairly similar with each other. At least that's what I believe what molality is. Let's see. Yep, exactly. It's the smaller m. Yep, moles per liter. I mean moles per kilogram of solvent. I like the way they say it better there, because the moles, exactly, the moles in both situations are always referred to as the solute. Okay, and the liter / the kilograms is a solvent. I like that better because, as I was mentioning with water, water typically is a solvent used, but don't be thrown off if you're given a different solvent. So that's why I just wanted to mention that, because of the fact that you have to be able to adjust based on the solvent they give you, because they could say like this was dissolved in 5 kilograms of acetic acid or something, but exactly, you just kind of solve it, make sure you keep your units all together, and exactly you'll be able to solve that question. But this is a key part of molality, is that it's using kilograms instead of liters. That is molarity, big M. Molality, small m, is moles per kilograms of solvent. Okay, so we'll move on to question 13 here. This is definitely correct because it even made sure that I was doing it correct. So, how do you determine the formula and molar mass of silver cyanide? So, how to determine formula and molar mass of silver cyanide? That is honestly a great question. How do you determine that? So, first we need to figure out what silver cyanide is made of. Okay? And unfortunately, I'm going to say a disclaimer right now, this is something you do have to memorize, because you won't be able to find cyanide on the periodic table, but you can definitely find silver on the periodic table, okay? So silver is just Ag, alright? Now silver is a strange one, but just the whole transition metals, but for this, I would actually say, because it's transition metal, you can't just really guess how many electrons it likes to give away. So we can actually do the same thing we did for copper earlier, but it's one element down. So what I'm referring to is the electron configuration, okay? So it's krypton, right? And let's actually draw out the orbital notation, because it's now 4D, because it's now one row lower, and it would now be 5s, because yep, 1, 2, 3, 5s, okay? Because you can see here, it's on the 5th row, okay? And it's going to be 5s2, or so we think in the beginning, and 4D, oops, sorry, 4D9, it seems. Because exactly, it's one more away from where cadmium should be. Now, if you remember what we discussed actually in the previous question, this is a fairly easy change for it to make. So it actually moved this over here, and now we can see a clear cut of how many electrons silver likes to give away, because silver would actually be written as krypton 4D10 5s1, because the fact that it's already so close filling its 4th D shell, so instead of just having that 5s2, it's just like give me an electron and bam, it's now a lot more stable. So its preferred electron to give away would be this, whoops, would be this 5s1 right here, only one electron. So silver typically as an ion would be Ag+, okay, just one. Now cyanide, like I mentioned, something you have to memorize, okay, is actually carbon and nitrogen. You may be able to figure that out based on the name, but I don't know. It's something that I just have to get really familiar with. So with that being said though, carbon and nitrogen, carbon likes 4 electrons, nitrogen is 5. So we assume the nitrogen works as a negative, because carbon is usually the positive one. So -5 plus 4. And then we know the total charge for this is going to be Cn minus. So silver cyanide really is AgCN. That's it. This is silver cyanide. Now the question asks for the molar mass silver cyanide as well. So for this, we actually have our work cut out for us, because only one element, one of each element. So one Ag, one carbon, and one nitrogen. So one silver times 107.87, carbon times 12.011, nitrogen times 14.007. Just going to equal each other. I'd like to just show all our steps so that we're not missing anything. Even though it may seem repetitive, you will definitely thank me later, because you will realize that sometimes when you're missing a part of a problem, it's better when you have everything laid out so that way you can find it quicker. 107.87 plus 12.011 plus 14.007. Whoops, what did I do? There we go. 133.888. So silver cyanide has a molar mass of 133.888 grams per mole. Okay, now as I said, with the cyanide part, it's something that unfortunately you do have to memorize. Now, because I haven't dealt with cyanide in a long time, there's a possibility that I may have solved this wrong, but hopefully I confidently solved this wrong, and that way I can at least adjust if this is actually not the right one. So let's see how we did. So definitely breaking it down more. Determine what type of bond is present. Prefixes are not used in silver cyanide, so they say it's an ionic bond. That is something that we should have mentioned. Not sure how it may have helped you, but silver is a transition metal, so that is going to be a metal and non-metal because it's carbon and nitrogen. I'm curious about that because I'm curious to see how they know what cyanide is. I think they just pulled it from a table. So they're just giving the basis for everything you have to do in terms of like how to cross multiply and simplify. This is just an example though. This is not actually what we're doing for this question. So there we go. It is an ionic compound. Okay, so they got that part right. The ions are silver and cyanide. So with that being said, they kind of just stated. I'm glad I was able to at least show how silver likes to lose one electron, and carbon, nitrogen overall has a net charge of -1. But yeah, exactly. So they do have AgCN, and they do the molar mass for each one. So they have just adding these three, and 107.87 is what I had for the periodic table. So exactly, there's a slight difference because they have 107.868. The point being is that they did get the right one, AgCN, yep, and they have a number close to mine, yep. So with that, this is correct. So that was a doozy of a question for number 13. So let's move on to question 14 now. Okay. Is CH3NH2 an acid or a base? This is a great question that we have to break down really. I mean, unless you saw the answer already. Is CH3, I do wish that was a little bit lower, but no worries. The point here is to explain why the answer is correct. That way you actually understand it. An acid or a base, okay? So let's actually, for this one, I like to usually draw out the actual molecular compound. So we have C, well, kind of just looks like this actually. Okay. But I feel like for this one, it'd actually be a lot better to understand if we drew the Lewis dot diagram as well. So we have C, okay, we have N, and we have a lot of H's in the middle, okay. And I did double check, we should have the exact amount of electrons needed, but just to double check that, we have 4 here, nitrogen gives 5, each hydrogen gives 1, so 4 plus 3 is 7, plus 2 is 9, plus 5, total should be 14 electrons. Okay, so how many do we have here? We have 2, 4, 6, 8, 10, 12, 14. So this checks out for Lewis dot diagram. So now the definition of a Bronsted-Lowry base is that it has, just to make sure, sorry, my eyes are a little itchy. It has a place to accept, like it has lone pairs, actually, which, funny enough, is exactly what nitrogen has. A big lone pair just right there. The reason why it's usually defined as having lone pairs is because what happens is that if there is a hydrogen proton wandering about, okay, it could actually attach to this lone pair. This nitrogen in itself, in a way, is receiving a proton. So then what we get, actually, when it's all said and done, and because this thing used to be neutral, right, and that proton brought its plus charge, we get this. Okay, and what this is, CH3NH3 plus, this right here. So because it can receive an acid, right, receive a proton, that by definition makes it a Bronsted-Lowry base, because it's, once again, it's getting this hydrogen and it's attaching to that lone pair. Okay, so see how we did. So exactly, upon reacting with water, so they actually provide like a actual compound that does have extra hydrogens for you to attach. So exactly, it shows that CH3NH2, it does act as a Bronsted-Lowry base because it's accepting the proton, which it can because it has a lone pair. Now with this, just as a quick disclaimer, you're probably wondering, but it has all these other hydrogens, like on the carbon side, why doesn't it give that away? Typically you'll notice that the hydrogen being given away is usually one attached to a hydrogen bond. Okay, so these two hydrogens exactly are attached to nitrogen through a hydrogen bond, because hydrogen bonds are between O, N, and F. Okay, those are the hydrogen bonds. But the thing is, though, is that nitrogen also wants to be a stable charged molecule as well. So if it were to lose one of those hydrogens, it would end up being quite unstable, not very pretty, something that it doesn't want to do. But if it gained a hydrogen, now it's actually kind of balancing out the situation, where it's like, although my charge is positive overall, I was able to now get another hydrogen bond, which is really what it likes. With carbon, those hydrogens are nonpolar bonds, each one of those bonds. Carbon does not play with these hydrogens. These hydrogens they're not active. They don't have any polarity or trying to look for the right word here, charge or net charge or anything, or where things are pulled together. Attraction forces, exactly. The only force really is just the Lewis dispersion force, and so those things don't get pulled to anything. They don't interact with anything. Hence why these hydrogens here they do not function as part of the whole acid base giving away thing. But these hydrogens have the potential to, okay? These hydrogens here have potential to interact. So once you get actually to this part, any of these hydrogens could leave. Any of them are fair game for it to go back to its base form. Because right now, this here, what we have is its conjugate acid, okay? But any of these hydrogens here could detach and put it back to its conjugate base form, okay? So with that, this is correct. Let's move on to the next question. Question 15. All right. Is acetic acid a weak acid or a strong acid? Why? So acetic, once again, if you see the answer, I'm definitely giving you a time to even read the explanation because that's very helpful. But I just have to write down the question first. So acetic acid, weak or strong? Why? So for this, actually, see, I have a lot of tabs open actually, so I can just refer to them. This is our acids and bases tab. So first, let's actually find out what acetic acid is. Acetic acid, okay, and its molecular structure, something that you do have to memorize, unfortunately, is CH3COOH, okay? So this is acetic acid. It would look kind of like that. This right here is acetic acid, okay? And we kind of see, because we don't know if it's a weak or a strong acid. The reason why is what I'm about to do. Once you find out, okay, this thing called Ka, which is the dissociation constant for acids, okay, then you're on something, okay? Then you can start to answer what the question is truly asking for. So with that being said, what does even dissociation constant means? It means when it's put in a solution, how much of it actually dissociates, forms into, like, for example, with acetic acid, how much of it forms this and that. This right here is what the dissociation constant is doing. So in fact, if I were to write down the whole equation, it would look like this. Okay? That is what it would look like. Alright? And you don't forget your aqueous solution. Alright? So that's what we're dealing with here. Now, Ka comes in many shapes and sizes, but you will never see a Ka that is less than 0, okay? Because 0 means that that thing is like, it does not dissolve. It's completely insoluble, that it will not separate at all. It's like kind of like putting like a chunk of metal in water. Even though that does technically get oxidated and rust and everything, that's kind of what we're dealing with here, where it's like it'll take a while for you to actually start seeing pieces mixed with the water. So 0 is like quite extreme, but that's like the lower limit of Ka, okay? Now there is limits in between, okay? Ka can range from 0 to infinity. That's what we're dealing with. But strong acids need a Ka, okay, to be greater than 1. Okay, anything with a Ka greater than 1, it means they're strong acids. So you can probably guess a weak acid, okay, and just because that just means that when you put it in water, it's going to like separate like completely. It doesn't, like, no part of it wants to stay together again. Good example is like when you put salt in water, unless it's like fully saturated, which is a whole different issue, that means there's literally no water left for the salt, it would just dissolve completely. It will form the Na plus ions and the chloride ions as well. So now weak acid is something that's not like salt, where it's like you put it in, only like parts of it dissolve. A lot of chemicals do that. You see like the solutions are usually like cloudy and stuff. That's what we're talking about here, where there is like some precipitate formed. So with that being said though, it's usually between 0 and 1. Okay, so it's like 10 to the minus 1, 10 to the minus 2. When you start dealing with decimals and such, it can get really small, and the smaller it is, the more insoluble or the less it dissociates. Insolubility is usually for like when you're dealing with solids. Dissociations when you're dealing with like aqueous solutions like these, where it's like you start with, you know, it's still liquid, like acetic acid is still liquid, but when it enters the forming acetate and hydrogen ions, that's where the issue is. So now let's look at the table finally to see where acetic acid sits. CH3COOH, acetic acid. It's like there we go. Acetic acid, 1.76 times 10 to the negative 5. Right away, you notice that it's definitely less than 1, but it's obviously greater than 0. So acetic acid, simply based on its dissociation constant Ka, is a weak acid because it does not dissociate completely. Example would be like hydrochloric acid, HCl, strong acid. Put that in water, you will literally only have Cl ions and H ions. You wouldn't have like HCl still floating around. Okay, let's see. Weak acid because exactly the Ka is times 10 to the negative 5. In fact, I'll just do that. I'll write the Ka as well, because that's actually how we found it. 1.8 times 10 to the negative 5. Because of that, it's a weak acid. Okay, so it talks about how it doesn't dissociate completely, and considering the acid dissociation constant is low, this is a weak acid. Anything really, as soon as you hit less than 1, you can just say it's a weak acid, just because that means it doesn't dissociate completely. Meaning that however much moles or concentration of acetic acid you have, or other weak acids, the acidity, like the pH value, would read higher than it would be of like the same concentration of a strong acid. And by higher, I mean it would appear less acidic, because exactly it didn't dissociate completely. Okay, so now let's move on to question 16 here. What are the balanced chemical equations for the following? Oh wow. Oh indeed. This is going to take us a little bit of time. So, with that being said, balanced chemical equations for the following. So when it comes to balancing equations, right, I'm just gonna actually list them all out, so bear with me here. A, B, it should be a way for me to actually snip this and paste it, make it a lot easier. So if I just did this to save us a little bit of time here. Okay, nice, it actually worked. So just exit out of this now, get back to our question. Okay, so we now have it nicely written down for us, and we're allowed to just go ahead and balance this. So the way we answer these questions is actually we want to make sure that the amount of I guess elements or properties in one side equal the amount of properties in the other side. So with that being said, we kind of have to go, I usually just bounce back and forth. There's probably a better way to do it, like when you list everything down. But you notice when you have molecules that are like bonded together, it's kind of usually better to just reciprocate the change on the other side as you go. So for this one, let's just start right away. We have FeCl and iron chloride, okay? And we notice that it's Cl3. So for this to balance it out, the 3 needs to be here. We need 3 chlorines to make up for the FeCl3. And we don't bother putting and oh, that's interesting actually. For this one, because interesting. I'm gonna add some extra parts to this because I personally do not like how it's written. You will rarely see. Don't worry, I'm gonna erase that 3 after. Just want to make sure that it's big enough to where we can actually work with it. But I don't want to cover my question. So the reason why I didn't like that is because Fe would actually have a charge with this. So I don't know if they're supposed to do this, but because chlorine gas usually comes in as a gas with like Cl2. This is typically what chlorine would be. So I think they're referring that it's going to be an ion. And the same with this one as well. And these are both ions. So with that, now I can just put the 3 in front of this, okay? It didn't really work at first because if we're dealing with chlorine gas, this whole thing would look quite different. But I'm not sure if they want us to add the subscripts. Usually you don't touch subscripts. Okay. Well, I guess they do want us to touch subscripts. Because in this case, they gave us O2. And they still gave us Fe without a charge. I'm not liking that one bit. So I'm just gonna leave this one as is and just solve it. So it says that we have 2 Fe's, right? So 2 here. We have 2 oxygens here, but 3 oxygens here. So we need the smallest common multiplier, which would be 6. So it'd be 3 oxygens here and 2 of the whole of the whole molecule. But because we just did that, Fe2 has to be changed because now we have 2 Fe2, so this actually becomes 4. Okay, so let's move on now. That's will be how you solve that one. For this one, exactly like I said, I kind of like to go I don't usually list everything at once because I like to go like one piece at a time. And for this one, I also like to note what type of reaction it is. So this one is like a combination. It just helps me keep track of things. This one's also a combination. So a combination is 2 things becoming 1. Okay. This one is a double substitution. Okay. Because you notice that it was FeBr3 and H2SO4. But now they both switch their partners in a sense. So we have the SO4 here, right? But now we have 3 of them here. So we need at least 3 SO4 here. But because it was 3, but it's H2, right? We need 6 hydrogens in total. So there we go. And now because we have 6 hydrogens in total, let me make sure I'm doing this right. Yep, because we have 6 hydrogens in total, we need to balance out the bromine. So bromine actually needs 2 here. Okay. But now you notice that now we need 2 of these. Okay. But now as you notice, this is going to turn into SO4 times 3. We need 6 of these. Oh, is this even possible to balance? Because then when you double that, this also changes. Let me think about this one. Let me start first by just doubling the FeBr3, or maybe it's just looking for 3HBr. Because now it would be 3, but H2SO4. So let me just make this 3, make this 6, because you can't. Maybe it's half. No, that wouldn't work. 3. Or you have to now do this by the. I think it's asking us to balance, because some of these might be balancing through the, what's that called? The redox reactions. But I'm not sure. Let's actually see first, okay? Because SO4 is typically 2 minus, okay? And there's 2 of them, so that's minus 6 in total. Oh, yep. So now this has to be plus 6. And that means this has to be plus 6. And then, yep, this is still minus 2. Minus 2 plus 2. Hydrogen is plus 1, and then the FeBr here, so that is so this is not a double substitution, this is actually a redox reaction. Redox, okay? So, wow, well this is gonna be a fun list to go through. I want to enjoy this one. Where is it? And because Br3 is usually minus 1, plus 3, plus 3. So because it's a redox, you notice, and the reason why I say it's a redox because this iron here changed from plus 3, okay, to plus 6. And does that even happen in redox? Let me see. Redox reaction of this. Does iron ever go from plus 3 to plus 6? Let's see. Oh no, I just want the list. Redox reaction equations. Nope. Redox reaction half equations. Okay, there we go. Half reactions, please. I just want the nice generous list, because I'll probably save it after this. Redox reactions half equations sheet. I'm just gonna try this again. This is strange. There we go. Something like this. This is what I'm looking for. Nope. Where is a good place I can look at this? I don't know why they can't just give a good list. Okay, well, I'll just look at this list in this picture here. Hopefully we can read it. It's a little bit small for my taste. We have iron. We have iron here. And we have iron there for Fe2 plus, Fe3 plus. I don't know if they even balanced this right. Because if anything, it should be Fe2SO4. Because if I type in, oh, this whole question might be a mess. Because if I type in iron, so I've never seen iron go from +3 to +6. But if I said iron sulfate, if I said iron 3 sulfate, because it looks like it is. Yeah, Fe2SO43. Wow. So they give us yeah. Okay. We're gonna go through these, but we're gonna really we're gonna just ignore every possibility of a redox reaction. So we're just gonna say that it is still a double substitution. And we're balancing this. We're gonna also change, this is now, I'm gonna state this right now very clearly, that you don't typically do this. Actually, let me just see if there is a, so Fe3 plus 2 Fe6. Yeah, no, that is, yeah, no. Yeah, no, it can't go to 6 plus. So I knew something was off. Back to this question though. So we want a nice 2 right there, because that's actually what, so this thing just might have a bunch of issues with it. So when we're balancing this out, we're going to be really liberal and just, I guess, adding whatever we please, at least in terms of what makes sense in the real world. Typically, the only thing you'll be changing, as they indicated, is, you know, the part in front, the not the subscript, but in terms of like the prefix, that value there, that's usually what you should be changing. But we need this here because I've never seen that type of sulfate before. It's usually iron 3 sulfate, which is Fe2SO43. Okay, so now back to that, when we actually try to balance it out, this no longer is an issue. Okay, you get 2, 6 there, 3, and now this is 1, because exactly now 2 is right there. And as you notice, just want to add it nicely there. As you know, exactly 2 Fe check, 6 Br check, 6 H check, 3 SO4 check. So this is what was missing. So let's keep our eyes open out for any other situations like that. So C4H6O3 plus H2O, C2H4O2. So for this one, we want to start by maybe doubling this, because that's the only way for it to have 4 oxygens like the other side. Okay, so now we have 4 carbons, check, 8 hydrogens, which, yep, 6 plus 2, 8, and 4 oxygens. Yep, that's correct. That's all you have to do. And now let's move on. C2H4 plus O2 equals CO2 plus H2O. So this one's actually a combustion, and this one again is a formation. That's the same thing as combination, really. But to keep consistent, I'm going to name all of them formation. Okay, combustion, you know, reacts with oxygen to form CO2 plus H2O. This one, the last thing you want to balance is the oxygen, because as you can see, it comes from 2 different parts. So, with that being said though, so I guess for even the question prior, it would have been better to start with the carbons, okay, because that's the only one that doesn't come from 2 places. So by doubling that to match 2C2, everything just happened to match as well, which was good. So for this one, let's start again with the carbons, because they only come from 1 place. So C2 here, so we need 2 of these, right? And now the hydrogens, we have 4. So H2, we need 2 at least, okay? So we have 2C, which is C2, and 2H2, which is 4H, okay? And now we need to find out how much oxygen that is in total. So 2 of O2, so that means at least 2, plus 2O, that's a third of O2, because there's going to be 2 here and 4 there, so that's 6 in total, so that's 3 O2. So that's why we did the oxygen last, because it would have been really hard to balance based on just the oxygen alone. So now this one's another combustion, okay, and we have start with the carbons again, C4, so that's 2 over here. Oops, sorry, definitely miscounted. That's 4 over here, okay, and H10, so that's 5 over here. And now it does have an awkward extra oxygen. This is where it gets complicated, because now we're dealing with that one extra oxygen. So first, let's see if we don't have to make any changes and double anything. So right now we have 4 CO2, so that's 8 oxygens there, plus 5, so that's 13. So if we subtract that one lone one, that's 12, which is good because actually what we want, one even number, when we subtract that one oxygen. And so 12 divided by 2, that's 6. So this actually should work, because we have 12, 13 right there, and 8, yep, plus 5, 13 as well, 10 hydrogens, 4 carbons. Now this one is also another combustion. Okay, so yes, this one was just written wrong. It looks like now they're making a lot more sense. C2H17, so that's 2 carbon here. Oh wow, that's not even possible. Well, we're just gonna solve it as it is, because the reason I say C2H17 is impossible is because carbon literally runs out of bonding space. It can only fit maximum 6. Maybe that's supposed to be a 7, but that even wouldn't be enough. It needs at least 8. At least 8. Let me see even what they even have for the answer. I don't even. Yeah. Okay, I mean, sure. With this imaginary made up molecule here, H17, meaning that we need to double this actually, because hydrogen comes in pairs, so you can't have half of it. So it'd be 17 H2O here, 4 carbon there. And the reason why we double it exactly is because you want to make sure that you can actually put a whole number in your brackets. So that's 17. I'm going to have to double a lot of things. 17 oxygens, okay, plus 8. So 17 plus 8 is 25. Once again, you can't do 25 over 2. So what you really need to do is now make this 25, yes, but that means everything got doubled to make up for it. So now we have 50 oxygens, okay? And to make sure that we have 50 oxygens, that's what we get. So now we have 16 from here, plus 34 from there, and we have 34H2, which is going to be 34 times 2, which is 17 times 4. So all this makes sense. I am not the biggest fan of these questions, but we're going to just get through these. I might call it a night after this one, only because this was definitely a question that was a lot more, I guess. Actually, no, we'll keep going after this. Maybe get more in the zone after this one. But let's see. H2SiCl2, H2O, And so for this one, you notice the only thing that doesn't really move around is a silicon. So there's 4 of them here, so we want at least 4 here. Okay. And what else does not? Well, I mean, the chlorine only moves to one spot. It's not split between 2 things. So if we have 4 of Cl2, that's 8 in total. So that's 8 HCl. Okay. So now let's see if everything else can balance out. So let's not touch the... Oh, we don't need to touch the hydrogen yet, because the oxygen we can actually balance first. So there's only 4 oxygens here. So for this, it would be 4 H2O. So let's see actually if all the hydrogens balance out. 8 plus 8. So let's see the hydrogens. That's 16 hydrogens in total. And 4 times 2 is 8. 4 times 2 is 8. So this checks out actually. And this is what we'd consider H2O to HCl. I guess this may be a double substitution, although it's not as clear because a lot of things changed. Yeah. So now for this one, what is this? They have zeros in there and ones, or is that 10? I think that is 10, 10, and 15. Interesting. Okay, let's just assume that's 10 then. Okay, so this is a 10, and silicon doesn't move, so we assume that this at least has 10. Okay, and oxygen 15, meaning that this is at least 15. Okay, so if we have 10, and then chlorine, I think this is also a double. It's the same thing as above, but just more complicated. So 10, 3, that's 30. Okay. So with that logic, we should have 30 plus 10. We should have 40 in total of hydrogens. So 15 times 2, yep, 30 plus 10, 40. So this works. 15, 15, 1, and 30. And now this one is going to be, I don't even know anymore. I'm going to start naming them because let's see how this one moves. So the goodies of the carbon stay the same. Okay, they don't move. The NO3 becomes NO2. But we know that at least there's 3 of them. So it needs to shed, I guess, that amount. But wow, this has been an overall headache. Maybe we don't need to touch this because the C7 stays similar, but let's see now what happens in regards to our number of oxygens. So we have 3 times 3, we have 9 oxygens there, so 3 times 6 here, that's only, 3 times 2 here is only 6, so assume this has to be 3. Okay, now to really find out that's the case, we need to add all the hydrogens. So 3H2, that's 6 hydrogens there, plus 6 hydrogens there, so that's 12 hydrogens in total. 9 here, plus 3, that's also 12 hydrogens. So we balance that one out. I think these ones might just be made up, but not really my favorite type of question, because especially when they're elements that can't feasibly exist, it kind of just ruins the whole point of it, in my opinion, just because at that point it's like, what am I balancing? I like to usually conceptualize and visualize the actual molecules and how they interact with each other. So having things like C2H17 that doesn't really work in a natural state, it can be quite confusing. But with that, let's just move on. Let's see what we have here. We have only 1 sodium, so we have to change anything. 1 chloride, it looks like, but C5H8O2. We have only 1 O2. So what changed? H8. So that's 8 plus 9 plus 10. went to 12. But the carbons stayed the same. So the only way for that to happen is if these two were to double. And that's it. Because now we have 8 plus 9 plus 10 plus 11 plus 12, which is each 12 right there. Okay. At this point, it's kind of just like I'll solve it as I go. I wish I could explain more, but because these things weren't like typical, real, actual equations, it made things a lot more complicated. So back to the top. Let's see how we did. See, I don't understand that because exactly they just assumed, it seems, that chlorine was actually not an ion but a gas, which you can do as well, but it would say Cl2 right there. They didn't even notify it, but 3Cl2 is the only way this balances out for 6, and exactly. So that is what they assumed there, which is why they have 2 plus 3 goes to 2. But I'm going to leave it as the ion because that is definitely a viable option as well, considering that it didn't specify. So 4, 3, and 2, we got that right. 2, 3, 1, and 6 only works because I had to throw in that Fe2SO43. 1, 1, and 2, yep. 1, 3, 2, and 2, yep. 3, 2, 2. 6, 4, and 5, that's correct. 1, 11, 7, and 8. 7. So is that a C7? That still doesn't make sense. Yeah, no, that's because C7, H17. Because if you know, for a carbon, for it to be a full, it's going to be CnH2n plus 2, right? That's as full as it can go. So if it was carbon 7, it'd be H16 as its maximum, because it'd be 14 plus 2. So C7H17 still does not work. But that's the only thing that could happen because it says it has 7 carbons on the CO2. But it also, or did it say C7H16? Oh, that's so confusing because I think it just assumed it was H16. I'm not liking any of these whatsoever because, yeah, the reason why I say it's H16 is because they have 8 H2O here. So, yeah, I don't know if it's the question that's incorrect or the way the person solved it that's incorrect. Yeah, who knows? Let's see here. 4, 4, 1, 8, okay. 10, 15, 1, 30, okay. 3, and then 3, okay. And then 2, 2, 2. So, they make a table. They try to balance it out. I'm just going to skip down and say this is incorrect. Not sure if it's the question or the answers, but things do not add up. So that was definitely a question for sure. Let's move on to question 17. That just assume that doesn't exist anymore. And for the rest of these, we're kind of just gonna shimmy through them. I had a plan of trying to get through 30 questions today, but that one especially seemed to have eaten a lot of my time. So let's just continue to move on though. A sample of a compound oh, I almost forgot my water break. Oops. Try to do one every hour at least. Okay. A sample of a compound containing CO and silver weighed 1.372. So, sample containing CO and silver, okay, weighed 1.372 grams. All right. On analysis, it was found to contain 0.288 oxygen, well, grams of oxygen, and 0.974 grams of Ag. Okay. Molar mass of the compound, so 303.8 grams per mole is the molar mass. Actually, I shouldn't square that because it looks like an answer. Okay, what is the empirical and molecular formula for the compound? Okay, so a lot of information here. The way we solve this actually is that we actually want to figure out ratios. And you're probably thinking, oh yeah, ratios of the grams. No, you want the ratios of the moles actually. But you're so far only given 2 pieces. But because you're given 2, you can kind of tell how many grams of carbon there'll be. So you started out with 1.372, right? You subtract the grams of oxygen, 0.288, and you subtract the grams of silver, okay, 974. Whoops. 1.372. So you only have 0.11 grams of carbon. And now the next step is that you want to convert each of these into its molar mass, okay? So let's start with carbon. 0.11 grams of carbon. You want to multiply that by 12.011 because, I mean, not by its molar mass actually. The better thing is the atomic mass units, because you want to just get the moles of each one. Okay, and there, grams cancel out. Okay, so that's divided by 12.011, 0.0091. Okay, now for the oxygen, 0.288. Just gotta make sure I have the right numbers actually. Yep, 288 and 974. Okay, good. Grams of oxygen. Same thing, 1 mole, 15.999. Why did I not use the double of it? Because we're actually using only the atomic mass units. We can't assume that oxygen comes in pairs or anything, because this is just a molecule. We don't know the constitution. Okay, so that's 0.288 divided by 15.999, 0.018. Okay, and now for the last one, silver, 0.974 times silver now is actually quite big, 107.87 grams. Okay, 1 mole of silver. So let's actually write down what it is. So it's mole of carbon, mole of oxygen, and 0.974 divided by 107.87 equals 0.009. Okay, 90 mole of silver. Now you probably start to know something right away. Actually, you see that it's the ratios, right? You see the smallest number technically is a silver, but these two right here are quite close to each other. But point being, right, is that you want to get your smallest number and divide everything by your smallest number. So that's divided by 0.0090, 0.0090. So this one would actually just equal 1. Okay, so with this, 18 divided by that, it's 1.99, and you kind of just round it to 2 because you want to get the ratios, right, to get your empirical formula. And now for the last one, we want that divided by 1. Okay, so that's equal to 1.01, which you kind of just round to 1. So if we were to write the empirical formula based on these ratios here, actually, starting with the metal, before we go to non-metal, we have AgCO2. This right here is our empirical formula. It's the lowest multiple of it. Okay, and the reason why I say the lowest multiple of it, because exactly it's 112. And now you're probably wondering what we're going to do with this molar mass. You're actually going to find out how many of these AgCO2s fit into that 303 to find out the multiples of AgCO2 there is. Okay, so what we actually need to do is now get the mass of each one. So constituents, so Ag, that's 1, Ag, 1, C, 1, I mean not 1, sorry, 2, oh, okay, so it's times, we just have the numbers right there, 107.87 times 12.011 times 15.999, 107.87, 12.011, 31.998, and then we add them together. Okay, plus 107.87, 151.879 is what we get, grams per mole. So that means we want to get that 303.8 and divide it by that. So 303.8 divided by 151.879, and we get around 2. So that means our molecular formula is just double of that. And don't be mistaken, you don't want to add the 2 in front. You actually go Ag, because this is our molecular formula, right? You actually want to add them as subscripts. So Ag2, C2O4. This right here is our molecular formula. Okay? So that's what we have right there. So empirical formula, molecular formula is double of it. And you'll see that the math checks out because 303.8 is going to be the molecular formula. We only had 1.372 grams of it. So then because of that, this would be how many of, I guess, each part you would have. Because 1.372 grams of it is 372 divided by 303.8 is 0.04 moles of this. And exactly based on even the numbers we got, well, 0.045 because it's of Ag2, and so I mean of this molecule. I remember for every one of these molecules there's 2 silvers, which is how we got back to now the 0.09 moles. So every math checks out for this. So with that, let's see, step 1, you're given that they found carbon, which is good, that is correct. They found each moles, okay, and they divided by each other and they rounded. Yep, 2, 1, 1, good. So it's AgCO2, perfect for the empirical formula. And now they figured they only had 151.88, perfect. So there's a ratio of 2, and that means they got Ag2C2O4 for the molecular formula. Perfectly done. This is correct. A lot more streamlined than the previous question, so that's good to see. Now let's move on to question number 18. What is the electron configuration of a nickel? Oh, I'm glad we're practicing these. So with that, nickel's right here, okay? So if we want to use shorthand, because let me just actually write down the question first before I move on. Configuration of nickel. Okay, so with that being said, let's just do the shorthanded version because we know what each of these before the noble gas comes up. So we start with our third row, noble gas, argon, and because nickel's right here, we have 4s2, 4, whoops, not 4, because now we're in the D row, 3d, 1, 2, 3, 4, 5, 6, 7, 8. It's always good to just make sure. Now you're probably wondering if this one does the same thing as the other ones we saw earlier today. Whoops. 5, 6, 4s, 3d, 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 3d. Now my theory is actually no, and you'll see why soon. Remember how I said that, you know, 1 is fine, but 2 and more is kind of crazy. See, 3D goes 1, 2, 3, 4, 5, 6, 7, 8. Does it really want to get rid of its whole outer shell just to be able to fill those two? No. So with that, this is going to be the electron configuration of nickel. Well, actually, sorry, minor adjustment. I even did it down there. This would be, because you want to make sure you put your lowest number first. This right here would be electron configuration for nickel. Hopefully this one is correct. Let's see. So they put 4s2, 3d8. You want to make sure that your lowest number is always in front first. So this is technically incorrect. And the reason I say that is because I'm gonna stress it again. Make sure you have your numbers in order. This is definitely something they can put as one of the multiple choice answers where it looks so close to what you want, but is not. You want 3d8 before 4s2. So yeah, that's something you got to watch out for. Even I almost did it as well. So yes, keep an eye on that. So now question 19. Okay. Draw an electron dot structure for the cyanide ion. In aqueous solution, this ion interacts with H to form the acid. Should the acid formula written as HCN or CNH? Interesting. Okay, so for the cyanide ion, okay, we discussed this. It's C, and they also tell us there. So Lewis dot for Cn minus. Should it be HCN or CNH? Now, let's start with the Lewis dot. Okay, C. Carbon likes to have, well, not likes. Carbon has 4 valence electrons. Nitrogen has 5. Minus means they have 1 extra. So instead of it being 9, it would be 10 total electrons. So carbon, nitrogen, okay? You have 2, 4, 6, oops, I think I already did it, nope. Carbon, no, I definitely did overdo it. Okay, so let's try that again. Carbon, nitrogen, so Lewis dot. That's just first, they know they have a bond in there. Okay, and we need to now make up for still 10 of these. Okay, so if I did 2, 3, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then that extra one somewhere. So with this, it would actually be better if we had And the reason why I do it like this is because all these, as you can see here, each of them will bond with each other. And now we have actually, let me just make sure, because it should be one bond and then okay, and then it's 1, 2, 3. Carbon likes to have 4, so and nitrogen likes to have 1. Well, oops, because there's 2 bonds here, so 1, 2, 3, 4. So carbon's filled up for now, and 1, 2, 3, 4, 5, and there's an extra one, so just throw it on this side. So now, if we move 2 of these and 2 of these, okay, now it makes more sense in terms of what they did with the double bond. Okay, all right, and that makes more sense. And just to make sure, yep, this carbon had 1, 2, 3, 4, 5, 6. Well, actually, put opposite ends. Okay, and now we're going to actually find out their number, their electron number. So let's see, nitrogen prefers to have 5 electrons, so it has 5 minus 2 electrons from a lone pair, and then 6, 2 plus 6 over 2, so that equals 0. Perfect. And now carbon likes to have 4 minus 2 plus 6 over 2 as well, minus 1. So you notice that's where the negative comes from. So this would actually be our cyanide ion. Okay, so this is important, right? Because exactly when the hydrogen comes into bond, right, the hydrogen plus ion, the thing is that it wants, well, the HCN or CNH, we don't know yet, it wants to be able to make sure that it can resolve this -1 issue. So if we actually brought it into a closer picture, this right here is where the negative would be, and this would be neutral. As if you assign the numbers, it'd be 0, it'd be -1 here and 0 here. So the hydrogen, which is a +1, okay, H plus, I'm going to draw a different color, would actually want to resolve the negative on that side. So you actually would have H bonded there to C, and then the triple bond and the N. This would actually be HCN. And yes, should it be HCN or CNH? It should be HCN. That is correct. And just to make sure we have the same amount of electrons just in the first part, 2, 4, 6, 8, 10. Exactly, so that one's correct. So with that being said, 1, 2, 3, 4. Okay, I see what I did there now. Okay, yep, the negative is hovering over the carbon, and exactly the Lewis structure. The H plus ion interacts with a negative charge on the C atom, which we know because of when we did the whole what the electron number was. Okay, so that is it for this question, and yep, it is HCN, so this is correct. So let's move on to now question 20. 100 ml sample of 10 moles of NH3 has a Kb of 10 to the -5. What is the pH? Nice. So this one is a multi-step question where we do need ice tables and also need to make sure we know what we're solving for here. But first, let's just simply write down what the formula is, okay? So N well, the question actually. So 100 mil of 0.10 moles of NH3 has Kb of 1.8 times 10 to the negative 5. Okay, what is the pH? So for this, what I like to do is start by writing the equation. NH3, okay, plus H2O turns into NH4 plus OH minus. Now this is key because this tells you that it's working as a base. As we remember when we discussed earlier, NH3, it has that lone pair, attacks the hydrogen, and so we form that conjugate acid. This is important because Kb formula, okay, is going to be what's it called, conjugate acid and OH minus over, well, I guess it's HA over A. I guess, yeah, HA plus technically. So this is a Kb, right? Because you still have your reactants, your products over your reactants, okay? So we still want to do an ice table for this, okay? Initial change equilibrium. And we have the HA plus, let me put it closer, and OH minus, okay? So it says 100 mils of 0.10 moles per liter. We actually only need the concentration because you see here the Kb formula only uses concentration. So because of that, we only need that 0.10, okay? And now, okay, we want to find out how much it changed. So that would actually be, the initial for each other one would just be 0. Nothing is associated yet. That's how we mark it. Now the change is going to be minus x here, okay? Because whenever it loses whenever it loses something, these two gain that same amount that it lost, okay? So it'll be 0.10 minus x as a final part in equilibrium, and these two would just be x. Now, to see if we can use a shorthand version, let's see if the concentration is at least 1,000 times bigger than the Kb. So what we do is we do 0.1 over 1.8 times 10 to the negative 5 divided by 1.8 e negative 5. Okay, good. This 0.1 happens to be 5,000 times over, so that's 5,000 times minimum. So it's greater than 1,000 times over, meaning that we actually do our shorthand, that this change would actually just be still around 0.10. The x is so inconsequential that it kind of just phases out as it's not included. So our real formula now is just Kb is equal to x squared over 0.10. So we multiply 0.1 to the Kb, which we know is 1.8 times to the negative 5. So 1.8 e negative 5 times 0.1, and then you square root the whole thing. Okay, so then with that you get, let's see here, 0. Well, after solving everything, you multiply that together, you get x is equal to 0.0013. So yes, we were definitely right in saying that the amount was almost inconsequential. Subtract that from 0.1, when you round it, you still get around 0.10. Okay, so now we know how much HA plus was produced and also how much OH minus. So this is a concentration of OH minus. That's a part that's important because this allows us to calculate our pOH. But you're probably wondering, they say pH though. We'll get there, don't worry. So with that being said, we first want to turn this into pOH by doing the negative log of concentration of OH minus, okay? And what do we get? So negative log of the answer we just got, our pOH is equal to 2.87. Now, the relationship between pOH and pH is that pH plus pOH is equal to 14. So 14 minus pOH is equal to pH. So 14 minus that answer gives us our pH. So what is the pH of this question? The pH is equal to 11 points. We want to do two significant digits, and it's always after the after the decimal for pH. So 11.13. That's what it rounds up as. So that's a pH. So because if you notice exactly, NH3 works as a base, and that's why they gave us the KB. So when they give you the KB, just know that you actually find the concentration of your hydroxide ions. And when you find the concentration of your hydroxide ions, you actually find the pOH when you do the negative log part. Okay? And so to get to pH, you need to make sure you do 14 minus the answer you got. Okay? So with that, that is really all there is to this question. It was quite a bit of steps. Make sure you know how to do your ice table. Make sure you know how to make the question easier, so you don't have to do like the whole quadratic equation. Because exactly, when you subtract, let me even show you. When you subtract that answer you got for the concentration from 0.1, you get 0.0986, which rounds to 0.099. Which can also still just round to 0.1 depending on how you want to do it. So exactly, that change is almost inconsequential. So exactly. So they did this formula, which is actually what we did. Amazing. That's the first formula we started with. And we got our hydroxide ions. Good. They did the ice table, which is good. Initial change and equilibrium. And they did products of reactants. They did the KB, but they did not make it easier for them at all. Yeah, actually, and it's funny because we still get around the same answer, because we got 1.33 using the quadratic equation here, and we got 1.34. So as you can see, you can definitely use that estimating way as long as the difference is at least over 1,000. Okay, so now let's see what else they did. Exactly, now they see that concentration of OH is the 1.33 times 10 to the negative 3. Yep, negative log of that, pOH is 2.88, and then they did pH 14 minus pOH, and they got 11.12. I got 11.13. It's pretty much the same thing. Usually they give you a range of what to work with. So this is correct. So exactly, as I mentioned, you can definitely solve it using the quadratic equation as well. It just takes a little bit longer, which is why we have that simplifying rule if the difference is 1,000 or more between the concentration and your K value. So now this is question 21. Okay, what elements there are exceptions to electron configuration? You know what? Let's actually look at our periodic table. I think I'm starting to understand the ones that are exceptions. So, with that being said, actually, if you look at column 6, okay, because as you remember, that one was chromium, and that's the one that had the so exceptions to electron configuration. Okay, and for this one, I'm going to be honest, I'm only familiar with the ones in the D shell. I'm not really sure how the F shell works. We don't really seem to touch that from what I remember being taught. With exceptions, chromium, right? Remember when we started from the argon? Okay, it was 3D54S1, exact, because it was one away. 1, 2, 3, 4. Okay, it would used to be 3D4. So you can tell anything actually in the 6th column. So that includes molybdenum, tungsten, and seaborgium, most likely. That would be your so column 6 would be your first exceptions. And now same thing, you go over to column 11, right? And remember, copper was AR 3D10 4S1 because of just one change, just to be able to get that shell full. So it'll be column 11. Elements from column 11 as well would be exception to electron configuration. Those are the only two that I'm familiar with. If they include the for the lanthanum series and actinium series, I would assume that it's going to be 1 before 7. So 1, 2, 3, 4, 5, 6, 7. Nope, sorry, I counted wrong. 1, 2, 4, 5, 6, 7. So it'll be like maybe europium and americium, and maybe terbium and nobelium, I'm assuming. But I don't want to say those yet because let's just see what they say. So the elements are exceptions. The electric configuration rules are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So let's see what they have to say. So copper, silver, gold, and they also said chromium, copper. What's niobium? Oh, I don't know why that's included. Molybdenum. Yep, that one makes sense because it's part of that list. And then ruthenium. Where's ruthenium? There it is. I can't say why ruthenium is there. I'm gonna be real honest with you, because yeah, I can't say why it's there. Rhodium, that one also I can't say. Palladium, yeah, I can't say for that one either. Silver, yeah, that one makes sense because it's so close. Platinum, where's platinum? Right here. And gold. Interesting. I still think it's going to be mostly column 6 and column 11 based on how they broke down for the electron shell. But I may be completely wrong when it comes to that. Let's see. Some atoms, such as transition metals, and some elements in the lanthanide and actinide series do not adhere to Hund's rule, which is fair. Hund's rule states that every orbital must be singly occupied before any orbital is doubly occupied, while Pauli's principle is that no two electrons can have the same 4 electronic quantum numbers. Yeah, exactly. Using the figure above, the supposed electric configuration of these rules are followed, and the actual electric configuration for these elements are shown. So chromium, yep, that's what we did. That one makes sense. Copper, yep, makes sense as well. While I would prefer the order to be changed for it to be 3D10 then 4S1. Niobium, 5S2 4D3. You see, this one makes more sense because the d orbital is half filled, but it just says like, oh yeah, this one, the closer it gets, the more stable it will be. Same thing with this one. The closer the d orbital gets filled, the more stable. Same with that. And palladium literally does what we discussed that shouldn't happen. We just got rid of the whole orbital, because we tried that and said it was wrong. So this one I'm having a bit of an issue agreeing with or not. They are called exceptions for a reason. Silver, exactly, that one makes sense as we discussed, because it only needs to fill in one more. Platinum, the F14 part doesn't really matter, but exactly, like that one, it doesn't make sense. Why would they not just do 2 like the other one? Gold, yeah, that one makes sense because it only needs one more. Let me see, yeah, because platinum, I don't really understand why. In fact, what I'm going to do here is search up electron configuration platinum. Yeah, I can't tell you why. So this is correct. That's great. So I guess this just goes down, really boils down to just memorizing it. There seems to be no real concrete way of saying whether or not it would prefer a certain type of configuration. But I'll definitely look out for the ones, at least for me, the ones on column 6 and column 11 at least will set off alarms to say, okay, I need to be careful on how I navigate it. The rest of them, I guess, is kind of to your discretion, really. Let's move on to question 22 then. Okay. What is a molar mass of sodium sulfate? So molar mass of sodium sulfate. So to be able to find this question out, kind of like what we did earlier, we first need to figure out what exactly sodium sulfate is. So at least we know this part here, sodium, which is just Na. This is going to be our metal component, and it's just sodium, so Na. And you can use the where it is on the periodic table to say that it likes to give away 1 electron. You can also use the configuration as well. If you start with neon, it's just neon neon 3s1, and you see it here as well. So yes, it just likes to be 1 positive. And now sulfate, as discussed, because it ends with ATE, it's sulfur with a certain amount of oxygens. So first of all, we can say this is a nonmetal. So this is an ionic compound. Okay. So because I memorized it actually, okay, sulfate specifically is SO4 2-. Okay. And let's see actually if it works. Sulfur is like on the 16th column, so that's going to be 6. Well, first oxygen usually actually -2, so it's -8 there. So to have that charge, sulfur is a 6th column, so +6 +6. So I guess it really does balance out. So we have a 2- charge here though. So in order for this to balance out, we need 2 Na. So the actual molecular compound sodium sulfate, it will be Na2SO4. This is sodium sulfate, okay? So with that being said, they're asking for the molar mass. So get the constituents, 2Na, okay, times 22.990, 1 sulfur times 32.06, and 4 oxygen times 15.999. Okay, so with that being said, 2 times 22. 2 times 22.990. That's going to be 45.980, okay? 32.06. And 4 times 15.999. 63.996. Okay. 980. So we're going to add all these together to get the molar mass. So that's plus the 45 plus 32.06. And we got 142.036 grams per mole. So this right here is going to be your molar mass of sodium sulfate, okay? So let's see. Oh, that's weird. 45, 32. Did I do times 6? No. 4 times 15.999. Oh, geez. Yeah. I don't know why. It just looks so correct. But 16 times 4 is not 48. 16 times 4 is 64. Okay, so this is incorrect because I think it's 16 times 3. That's 48. Yep. Because 16 times 4 is 64. I was wondering why it looked different. But yeah, they almost got it. But they do have that its chemical formula is Na2SO4. So they did have that part right. But that's incorrect. Now let's solve question 23. Oh, wow. Back to back. More molar mass questions. At least some semblance of normalcy, hopefully. Molar mass of sulfuric acid. So actually, we just did sulfate. I remember when I discussed 8. So a sulfate ion, okay, is SO4 2 minus. Alright. So if we actually want to turn that into sulfuric acid, so you drop the 8 and add the ic acid. So sulfuric acid. You just need to add the protons accordingly, and each one is just plus 1. So it's 2 minus, so we need 2 hydrogens to make up for it. So it'll be H2SO4. This is sulfuric acid. And with that, actually, we kind of just take our work from the previous question, really, because we still have 4 oxygens. So times 15.999, which equals 63.996. And we still have 1 sulfur, times 32.06, which is 32.06. The key difference now is just that we have 2 hydrogen instead of, 2, not 2 sodiums. So that's 1.008. Okay. So then we get 2.016. So 63 plus 32.06 plus 2.016. We get, as the answer says right there, 98.0. Because we use slightly different numbers, we got 98.072 grams per mole for sulfuric acid. Okay, so that is a molar mass sulfuric acid. This time they did make sure that they got the right amount for the oxygen, so this is correct. And we kind of just, it went a lot fast because we had information from the prior question to make these comparisons. So with that, let's see what our last question for tonight is. is NaOH an acid or a base? No spoilers. You may have already seen it if you paused it, or you could have gone back and paused it right at that moment. But it says, is NaOH an acid or a base? So for this, you kind of have to get familiar with how most things attached to sodium like to dissociate. Like, so if we're working with like K values, right? So just K, we don't say Ka or just Kb, just a dissociation constant. It's like always going to be much greater than 1. Sodium in general doesn't stick to anything. It will just form as Na plus ion. Okay? So that's going to form just a positive, and this used to be neutral. To balance out, OH minus has to be negative. And now this is looking quite familiar, isn't it? Because this actually is going to be hydroxide, and you know when hydroxide is present in water, if we just had OH minus plus H2O, for example, you end up with H2O. So let's label actually. This would be its conjugate base, conjugate acid. So we have a big hint right there. We just go through the rest and we produce so it kind of just goes back and forth. For the point being, at least for the one we're looking at, the OH minus here, that turned to H2O there, okay, we can actually say that NaOH is going to be a base, because of the fact that when it dissociates, that's what happens. It, you know, attacks sorry, blanking my words, attacks a hydrogen to become you know, its conjugate acid. But now actually, if we want to go by the Bronsted-Lowry definition, right, we actually let's draw the Lewis dot diagram real quick. Okay, we have Na by itself because it gave up everything, the plus, and we have the OH, because remember, Na has 1 valence, oxygen has 6, hydrogen has 1, so in total that's 8. So it'll look kind of like this, okay? And this will be where the minus is, alright? Look at this right here. It has quite a bit of space and a reason for it to actually go towards being neutral, okay? Kind of like, remember the whole nitrogen situation? These are all hydrogen bonds, things that it really favors. So imagine having all these valence, all these lone pairs, right? Looking for another hydrogen bond so that way they can be more complete. So because NaOH creates ions, well, an ion that has lone pairs, you can also say by Bronsted-Lowry definitions, this is a Bronsted-Lowry base as well. So you can prove it both by just a formulaic example and also showing that it has all these lone pairs waiting for hydrogen to come by so you can grab it. Yeah. So with that being said, acids characterize the presence of hydrogen, while base characterize hydroxide. From the formula, NaOH dissociates to hydroxides, meaning it's a base. And exactly, as you just mentioned, elements from group 1 and 2 are most likely to form basic solutions. I don't really agree with that per se, but the concept is still there that, you know, elements from group 1 and 2 like to redissociate, but specifically sodium, that one has a high dissociation factor. Things like calcium and other group 2 elements kind of have a harder time dissociating, but sodium especially likes to dissociate a lot. This is still correct though, just because, yeah, they were able to answer that question. So they just put that, and now I think this is a good time to say, or at least to stop here for today. So with that, I'm gonna do that, and So once again, I just want to thank you for joining me this evening. I hope you had fun solving these questions as much as I did. With that, if you have any further questions, please check out the links in the description below. It was very nice hosting this, and I hope to see y'all again. Have a great evening. Okay.